Why are degrees of freedom, DoF, crucial for robot design? Imagine trying to reach for a glass on a cluttered table without knocking over anything. How many ways can your arm move to do that? That's where degrees of freedom come into play. They are the key to understanding how a robot moves and performs tasks. Degrees of freedom describe how many independent movements a robot can make. Think of them as the different ways a robot can shift or turn. For example, moving forward and backward is one degree of freedom, while turning around a vertical axis is another. Each movement that can happen separately adds to the total degrees of freedom. In robot design, the number of degrees of freedom determines how flexible and capable a robot is. If a robot has only a few degrees of freedom, it can do simple tasks like moving in straight lines. But if it has more, it can reach around objects, change its orientation, and perform complex actions. For instance, a robot arm with 6 joints has 6 degrees of freedom, allowing it to position its end effector anywhere in space and rotate it in any direction. Having more degrees of freedom means a robot can reach more places and do more things. It can access a larger workspace, which is the total area it can reach. This is especially important in tight spaces like inside a car engine or during delicate surgeries. The more freedom a robot has, the better it can adapt to different tasks and environments. Higher degrees of freedom also help with task complexity. For tasks like welding or painting, the robot needs to approach from specific angles. Extra degrees of freedom give it the ability to position tools precisely and change angles quickly. This makes the robot more versatile and capable of handling intricate jobs. Another benefit of more degrees of freedom is motion planning. Robots with many joints can find smoother paths around obstacles. This flexibility helps avoid collisions and makes movements safer and more efficient. For example, in crowded factories, a robot can adjust its joints to go around objects without stopping or reprogramming. Kinematic redundancy is another aspect. When a robot has more degrees of freedom than needed, it can choose different joint configurations to reach the same point. This can improve stability, reduce energy use, and make movements more precise. But too many degrees of freedom can make control more complicated. It requires advanced algorithms to coordinate all joints properly. Control and programming become more challenging with higher degrees of freedom. More joints mean more calculations for movement paths and collision avoidance. This can increase costs and maintenance needs. That's why designers carefully choose the right number of degrees of freedom based on what the robot needs to do. In industrial settings, robots often have 6 degrees of freedom. This allows full control over position and orientation of tools. For simpler tasks, like pick-and-place operations, fewer degrees of freedom might be enough. For collaborative robots working alongside humans, fewer joints can make programming easier while still being effective. In the end, degrees of freedom shape what a robot can do. They determine how well it can reach, manipulate, and perform tasks in its environment. Finding the right balance between capability and complexity is essential for designing effective robots. Understanding how degrees of freedom work helps engineers create robots that are both powerful and manageable for their specific jobs.